That's why we can have the the EMF in the output. One can see that when sun gives the energy, sunlight photons, when they incident on the PN junction diode, the charge carriers, the positive and negative charges at the junction, they will be separated, and we can have the maximum value in the meter. Right? This is just a schematic idea how does it work. Now on the left hand side we can have the construction of the PN junction of this particular PN junction diode. Generally solar cells are made up of silicon, and you can see the upper layer is the glass cover, the second layer is anti-reflective coating, then the third one is the contact grid, that is the terminals. In between that silicon layers are there. P-type and N-type silicon materials are coated in between these two layers, and at the end there is a metal backing. On the right hand side we can see a solar panel diagram. One can have the load at the output, so it can work as the EMF. This is actually one of the applications that we can have. When sunlight increases and the photons are incident, the electron flow will be there due to the charge separation. Electron flow will be in one direction and the whole flow will be in the second direction, and whenever these two are in opposite direction, they will be accumulated at opposite layers, on N-type layer and on P-type layer, and due to this accumulation of charges, there will be a charge separation, and in the output we can have the EMF. Now here is another look at how does the current flow in solar cell. One can have the photons again, and it is actually more elaboratingly it is explained that when photons incident on the solar panel, the current flow direction is in one direction, and the positive contact will have the one side of one type of charges. On the another side there will be another type of charges, and due to that the electrons and holes, they will be having the opposite direction of motion, and due to that we can have the EMF in the outermost circuit. Here is the power curve and VI characteristics of the solar cell. One can say that what is VI characteristics? It is actually a voltage versus current graph. The first one, that is, here we can see that this is actually the VI characteristics. It shows that at a particular value ISC, at that point the voltage is 0. That is, when the solar cell is short circuited, the voltage is 0 and ISC can be measured at the as a short circuit current. And here we can see the another point, that is called VOC. VOC, it is the open circuit voltage. At that point the current is 0, and at a particular in that particular graph, the second curve, it shows the power curve. Power curve is the graph of power versus voltage. The power that we are getting, that is plotted against the voltage, and here we can easily find out the maximum power. That point is called maximum power point, or P max or PMPP. From that, if we plot, if we just make a diagram, if we plot it on the V axis, on the voltage axis, we can get the VMPP point. That is, at that particular voltage we can have the maximum power from the solar cell. And if we plot, if we find out the intersection of this line, this normal, with VI characteristics, we can have the same MPP, maximum power point, on VI characteristics, and if we plot it on Y axis, then we can have the maximum current. This IMPP and VMPP play a major role in terms of determination of the efficiency of the solar cell, and these two curves, the VI characteristics and the power curve, they give the maximum information about the given solar cell. So whenever one solar cell is used in any type of the applications, these two curves are to be plotted before joining the solar cell into the application. Now what are the this is actually the different again power curve and VI characteristics, but it is at different illuminations. One can see here, with the increasing illumination the current increases and of course the power also increases, right? So excuse me. The main 4 parameters of any of the solar cell is open circuit voltage, short circuit current, fill factor and conversion efficiency. Open circuit voltage, that is VOC, short circuit current, that is ISC, fill factor FF and conversion efficiency is denoted as eta. These 4 are the major parameters for any of the solar cell. Now what is ISC? ISC, it is the short circuited current and it is through the solar cell, it is current through the solar cell when the voltage across the solar cell is 0. As I said that when the solar cell is short circuited, one can find it out from VI characteristics that it is going to be have ISC value on the VI characteristics, right? The next one is I total. The equation for the total current I total is given here. It is I total equal to I0 e raised to qv by kt minus 1 minus IL. IL is the illumination current, and at V equal to 0 to I total will be equal to minus IL, that is equal to ISC. The short circuit current is the largest current which may be drawn from the solar cell. It is the maximum current that can be taken as the output from the solar cell. Now what is VOC? VOC is the open circuit voltage, that is the maximum voltage available from a solar cell, and it occurs at a 0 current. One can have a look at in the graph. We can see the VOC point here, right here. We can see that at that time the current is 0. It corresponds to the amount of the forward bias on the solar cell junction due to illumination. Due to the illumination, due to the photons, light photons incident, the solar cell is illuminated, and due to that it can work as an EMF provider. It can work as a battery. And again here in I total will have the same equation. So VOC will have KT upon Q ln IL upon I0 plus 1. So with this equation, if we can measure the current in the output, we can find out VOC. Now what is PM? That is the maximum power point, right? So we can have the maximum power point on the VI characteristics as well as on the power curve. It is actually the power output of a solar cell increases with the voltage, as we have seen in the graph and in animation. It reaches a maximum point and then decreases again. PM is IM cross VM, and we get a DC power from the solar cell, right? So here we can see that on the power curve we can have the P maximum as the maximum power point as an MPP, and PM is what ultimately it is I max into Vmax. Now what is fill factor? It is actually the measure of the solar cell, one of the major parameters of the solar cell. What does ideal diode curve says? The ideal solar cell should have a constant current, and at a particular voltage it should be 0, right? But we are getting the curved curve at a particular point in a real diode. So we have some lacking here in terms of the power, right? So we can have two P maximums. This is ideal P maximum and this is actually the realistic one. So it is, the fill factor is defined as the ratio of the maximum power from the actual solar cell to the maximum power from an ideal solar cell. So graphically FF is a measure of the squareness of the solar cell. Actually here we can see that FF is equal to maximum power from the real cell to maximum power from the ideal cell, VMIM upon VOC ISC. ISC and VOC, those are the 2 points, those are the two values which gives the idealistic values. ISC VM voltage 0, VOC, current 0. So they will give the idealistic view of the solar cell, but in reality we are getting PM as our maximum power point, and corresponding to that IM and VM, they are the realistic current and voltage. So we can have fill factor as the ratio of the real power to the ideal power. So this gives an idea that in realistic situations how the solar cell will work. And the next one is eta, that is the efficiency. It is defined as the ratio of energy output from the solar cell to the input energy from the sun. So it gives the direct value of the energy conversion. One can have eta as the maximum cell power divided by incident light intensity VMIM upon P input. P input is VMIM can be found, or in another way eta can be used as VOC into ISC into fill factor divided by P input. The efficiency is the most commonly used parameter to compare the performance of one solar cell to the another. And the most important point is that efficiency of a cell also depends upon the solar spectrum, intensity of sunlight, and the temperature of the solar cell, and that's why the efficiency decreases at the morning time and evening time. Also it decreases when the atmosphere is cloudy. So the sunlight intensity as well as the area in which we are using solar cell, that actually matters for the efficiency. Now what are the applications of the solar cell? These are some of the applications. Actually number of applications are there using the solar panel. Using the solar energy we can have a car, a bag. It is actually, bag is an innovative idea to use the solar panel as in a bag. One can have the energy, one can save that energy that is generated due to this particular solar panel, and one can charge numerous number of say devices. We can have the solar panels on the roof of our houses, and we can use that energy, that generated energy, in our household things to cook, or as a water heater. In the deserts one can have the solar panels here on the back of a camel, and one can use the simply given source, that energy source, that is the sun. Of course solar powered calculators we are using. We can use it in the robot. Then we can charge the mobile with the solar panel. The series of solar panels that we can generate in our planar areas, and a very large output of energy that can be generated from those. If we join them in series or parallel, we can have different outputs in terms of current or different outputs in terms of voltage, and we can, depending upon the applications that we are going to use it, we can have the different compositions of the circuit, right? So this is another application. The third one is of course solar water heater. Nowadays it is popular. The next one is the satellite power. In space, when we don't have any specific energy source, we have the most important, most significant source of energy, the sun, and the sun can be used there as the source of energy on the satellite wings if the solar panels are attached, and they are used as the source to generate the EMF to be used inside the satellite. The next one is the street light. Actually on the daytime the solar cell generates the energy, and in the night time the street lights can be used for the lighting of the streets, right? So this can be also used as street light, or even in the household lights also. There is one village in our Gujarat itself that is actually totally using the solar light as their source of energy. It is totally dependent on the solar light to generate the energy of that particular village, that is totally solar powered village. The next application is again the more efficient way to use the solar panels. Instead of using only one solar panel on one pole, they have used 5 solar panels with different orientations. The next topic is Hall effect. When a current carrying conductor is subjected to a perpendicular magnetic field, a potential difference is produced in a direction normal to both the magnetic field and the current direction. So what does that mean? It says that this is called the Hall effect. It says that when a current carrying when a conductor, the semiconducting material, is provided with an electric field, there will be a current flowing through it, and there will be, if we provide a perpendicular magnetic field, there will be a potential difference which is produced. Why? Let's see. Now this is the pictorial representation of Hall effect. It was invented by Edwin H. Hall in 1879. We can see here that the current is flowing in this direction, the magnetic field, it is in a perpendicular direction, and the voltage that is induced, that is on this direction. So here we can see the potential developed in another direction, the voltage that is developed, that is perpendicular to both current and magnetic field. Now what are the applications? We will study how does Hall effect work in a few minutes, but what are the major applications? We can determine the type of semiconductors, we can have the sign of majority charge carriers, that is whether it is p type or n type semiconductor, we can find out, and also we can find out the majority charge carrier concentration, that is Ne or Np. The last but not the least, we can find out the mobility of the majority charge carrier using the semiconducting material, right? So now we are moving to the paper and pen, and we can have the idea how originally Hall effect works. See, as we have seen in the animation, that